Welcome to Chemistry 111. I'd like to start real quick by showing you the solubility chart that I was talking about the other day. I posted it onto the Google Classroom. This is what I'll be giving you come test time rather than having you memorize the rules. The idea here is that if you can read this and utilize this, you don't need to really learn the rules. This fits with the rules pretty well. So to read this, on the left and right side, you see cations. The left side, you see the cation name. And on the right side, you see the cation elemental symbol or molecular formula. So if there's only one charge for that ion, they may not include the charge, such as aluminum. But if there's, say, more than one charge, such as copper 1 versus copper 2, they're going to show Cu1 plus versus Cu2 plus. We also have ammonium as a structure. But so we have on that. On the top and bottom, we have the anions. Most of them are oxyanions, but there's a deal of them that you have bromide and chloride and iodide in there, and sulfide and oxide. Some of these we didn't actually even really get to in the rules. So this actually includes a little bit more data. And so how to read this? There in the top left corner, you see the little designation. See S/I dash S/I and D. So this actually has a little bit more information. S does not mean solid. S in this case means soluble, so it will dissolve. I means insoluble or will precipitate. S/I means it's partially soluble, and we're not really going to deal with that. It means it will dissolve, but not very well. And we're not going to really deal with those problems. The dashes just mean it doesn't exist. There's no such structure. There's no, for example, aluminum carbonate. There's no known chemical formula of aluminum carbonate. Jeez. What the heck? Okay. And D means it would decompose rather than, so we typically won't deal with those as well. But just looking at that, so for example, if I had a compound like what we're going to get to, if I had, say, I'm going to put this on the doc cam here in a second. If I had something like cadmium, nitrate, and sodium chloride, and I asked, would a solid form? What would I have to do? If I just asked you with this, let me jump down to here, would a solid form? So the first thing you would have to do is swap ions, do a double displacement reaction. To do that, you're going to say, this guy's going to replace this guy. Look, nitrate is 1 minus, so cadmium must be 2 plus. Chloride is 1 minus, so sodium is 1 plus. So what you're going to see is you're going to have cadmium chloride and sodium nitrate. So there's our double displacement reaction. Now the next question becomes, well, are either of those a solid? So how would we go back to the chart? We're going to go back, flip back to the chart and look up. So cadmium over here, right here, cadmium cadmium chloride. Cadmium chloride right here is soluble. So that means it's aqueous. And then sodium, which is all these are alphabetically. Sodium, nitrate, sodium nitrate, soluble. So in this particular situation, going back to the dot cam again, both of these are aqueous. There would be no solid formation. There'd be no solid formation. So in a case where I don't even give you the products, how would you do that? You would split it, you would do the double displacement, and then use that chart. However, if I said, which of these ions might precipitate with a metal, which of these ions might which of these ions might precipitate in a solution of, for example, chloride, and I gave you four ions. You would just compare. Okay, on the chloride, which of these guys would be insoluble with chlorides? If I gave you copper 1 turns out to be insoluble. If I gave you, as I said, lead 2, lead was one of the situations that is insoluble. So solid, that one, but that one's actually S/I. But on the rules, it was just, we said insoluble. Mercury was another example of insoluble. Silver was another example of insoluble. But so if I gave you 4 or 5 compounds, you could look on here and compare it. If I matched it with this anion, which of these would be the least soluble? Which one of these has an I related to it? So if you can learn how to cross-reference this, that will be a pretty useful thing rather than trying to memorize a lot of rules. Those rules can be rather complicated. And one last exception, hydrogen plus hydroxide forms HOH, also known as water, H2O. Whenever you mix hydrogen and hydroxide, you form H2O. So it's neither soluble nor insoluble, it's the solvent. But okay, I just wanted to go through that real quick. So you'll at least have seen that. And that's posted on the useful information section on the classwork. So you can look at that at your earliest convenience. But okay. So part of this chapter is balancing equations. Part of this chapter is recognizing types of equations. And part of this chapter is actually writing the equation products and like trying to determine what is going on. Now, in order to really get a feel of what's going on, we need to be able to write a net ionic equation. So when we do a reaction, if there is ever an aqueous solution, the aqueous ions can be split apart. We write them together just for convenience sake, but in reality, they are actually floating around surrounded by water molecules. So when I say lead nitrate aqueous, that means there's a lead 2+ molecule and 2 different nitrate atoms floating around. When I say potassium chromate, it means there's going to be potassium ions and a chromate ion floating around. When I mix this together, I form potassium chromate solid, which sticks together like 2 Legos or like a magnet and essentially crystallizes out. It is no longer going to be floating around. It's now stuck in one place. Give enough time, it's going to settle to the bottom and you could filter it out. But the potassium ions and the nitrate ions are going to still be floating around. So the first thing we're going to need to be able to do is write a net ionic equation. The ionic equations are when we break down all the aqueous into the individual ions. So hopefully you'll notice that the nitrate and the potassium ions are the same on both sides. That you have potassium aqueous on the left, you have potassium aqueous on the right. You have nitrate aqueous on the left, you have nitrate aqueous on the right. And they remain just aqueous. These are what are called spectator ions. These are ions that don't change the state of matter, they don't change the charge, they simply float around observing the reactions. They don't actually do anything. Now, when we write a net ionic equation, what we're going to do is we're going to remove all spectator ions. We're going to separate all the spectators out to try to clear the way to show what is the driving force of this equation. What makes this reaction go? The net ionic equation shows only the ions and compounds that directly participate. So net, remember, if I made $500, but it cost a $250 investment, my net profits is 500 minus 250, or $250. In this case, if I started with these chemicals and these chemicals changed, I'm subtracting out everything that's the same on both sides to find what actually changed. The net ionic equation looks at what actually changes. Some equations will have no spectator ions because maybe everything gets involved. But some reactions may have all spectator ions, and that's the tricky thing. Whenever there's a situation where there's all spectator ions, we essentially say no reaction actually forms. No reaction actually happens. So in this case, silver nitrate plus sodium chloride goes to silver chloride solid, sodium and nitrate. If I subtract out the sodium and nitrate, the driving force is a silver ion bumps into a chloride ion, and you get silver chloride solid. The driving force is the precipitation. But in the case of potassium nitrate and calcium chloride goes to potassium chloride and calcium nitrate, we have no reaction. So I want to go back to the DocCam because I just did a problem just like this. So let's look at this. This guy is aqueous, this guy's aqueous. How we wrote this double displacement reaction is these guys swapped places. Writing these down on a piece of paper like this, it looks like we have a reaction. It looks like, well, clearly sodium is not near chloride anymore. Cadmium is not near nitrate anymore. They're floated around and do-si-doed and swap partners. But if we break this down into the ions, we see this would be cadmium 2 plus, 2 nitrate, 2 sodium, and 2 chloride. And the result is cadmium 2 plus, 2 chloride, 2 sodium, and 2 nitrate. All these guys are floating around separate from each other. All these guys are floating around separate from each other because in reality, they're all aqueous. We may write them adjacent to each other, but in reality, they're floating around in solution. They might bump into each other, but it's never a really long, meaningful relationship. Once they bump into each other, they float away. Nothing happens. So what the net result is, if I subtract everything out that is the same on top and bottom, we see there is no change. Everything gets canceled out. Everything gets canceled out. And so there's no net reaction in the long run. And that's one of the things we have to recognize. no solid is formed, no liquid is formed, no oxidation state is changed. We have no net reaction. We have no driving force. Another type of reaction that we can deal with net ionic is acid-base neutralizations. Remember, when acid and base neutralize, they're going to form water and a salt. Well, the salt is typically aqueous. And so if we subtract out the spectator ions, most acid-base reactions are going to just be H plus and OH minus goes to water. Most acid-base reactions are going to be just hydrogen plus hydroxide goes to water. Now, there are some cases with weak acids and weak bases because they are weak electrolytes. Even though we write these guys as aqueous, they do not fully dissociate. I will probably not throw this at you on a test, but you may see some of these problems on a homework. But a weak acid, hydrocyanic acid is a weak acid. Acetic acid is a weak acid. Rather than fully splitting into H plus and its anion, it stays largely together. So looking at the overall equation versus the net ion equation. Let's look at the DOCAM just to show that middle step that I've cut out. The middle step here is that when I went from this guy to aqueous, this guy to, let's see, water, and NaCN aqueous. Okay. The middle step is when I go to the ionic, this is largely stays the same because it's a weak acid. But this guy splits up into Na plus and OH minus because it's a strong base. Water, because it's a liquid, stays together. And we get into Na plus and Cn minus. Now, in the net, this guy, HCN, is different from this guy, so they don't get canceled out. But this guy is the same as this guy, so it does get canceled out. This guy is different from that guy, so it doesn't get canceled out. So between the net, it's just really HCN and OH minus goes to water and our cyanide. That's how we got the net. I just wanted to show all the work real quick. That essentially the HCN, by nature of its weakness, doesn't actually split apart. But, okay. And the last type of reaction is a redox reaction. A redox reaction, by definition, is a combination of oxidation and reduction. Reduction and oxidation together are abbreviated as a redox. Now, just like an acid and a base, acid-base neutralization, they need an acid and a base for it to work. If there's an acid and no base, it can't be an acid-base reaction. Well, the same thing here with redox. If there is there cannot be an oxidation without a reduction because of the nature of this push-pull relationship. An oxidation is defined as a loss of electrons, which increases the positive charge. A loss of electrons. A reduction, on the other hand, is a gain in electrons, which makes it less positive or more negative. We have reduced the charge. We have reduced the charge. We've made it less, and thus going into the negative realm. What is happening is one element is giving away some electrons. The electrons are being excited away from the atom. And instead of shooting off into the air to be dissipated and lost, it is then being absorbed by an adjacent atom, which then gains said electrons. Now, you got to remember, it's going to come from the valence shell, all that stuff, but we don't need to really worry about that so much when we're thinking about these reactions. But what's a good way to remember this? It's a mnemonic called oil rig. Oxidation is loss, reduction is gain. Oxidation is loss, reduction is gain. But they must happen in conjunction. If electron is being lost, it has to go somewhere. If you cannot find a place where the electron is going, maybe there isn't actually being an electron lost. So think carefully when we're making a statement that it is oxidation reduction. There should always be a matching pair. But if you really, really think there is a loss, look carefully. The other one may be a little bit more hidden. Now, how do we determine if a redox reaction happens? There are some rules that we can use to find the oxidation number of any element. Some of these rules we already know. Some of these rules are directly obvious. So before you go like, oh God, there's this huge block of text here, we'll break it down one by one and just look at this. In order to find a redox, you must find the charge of each atom and then say, is the charge changing? Is the charge changing? So we'll use some of these rules to help us. But rule one is a no-duh one. Don't forget this one. A pure element or a diatomic gas made up of just one element is always zero. So if I just said N2, the charge of nitrogen is zero. If I said copper solid, the charge of copper is zero. If I say like O3, ozone, the charge of the three oxygens are zero. Any pure element, which is the element by itself, and no other elements, is considered to be zero. We've kind of known that. It's because you can't have a charge if there's no charge. And you can't like have unequal sharing if there's nothing to share with. Number two is also a pretty no-duh one. If there is an ion and it has a stated charge, the ion is itself that charge. If I say there's a copper 2+ ion, the charge of copper is 2+. Don't look a gift horse in the mouth. If I tell you the charge of this is what? If I say there's chloride floating around, well, then that's chloride 1-, and that's so the charge of chlorine is 1-. Now, here's where it gets a little tricky. But so breaking this down, the sum of the oxidation states in a formula is equal to the overall charge. So what does that mean? In a compound like OH-, the compound like OH-, the charge of oxygen and the charge of hydrogen have to add up to give you -1. So whatever oxygen is and whatever hydrogen is, they will add together to give you -1. Now, the next two are usually rules. Hydrogen is usually +1 in a compound. unless it's bound directly to a metal, which is not going to often be seen. So really, hydrogen is almost always +1. Oxygen is usually -2 in a compound. There is one exception with hydrogen in peroxides, most often seen in hydrogen peroxide. But other than that, it is almost always 2-. Using that in mind, let's match that to what we just said about the OH-. OH-. The sum of these two must add up to -1. If oxygen is almost always 2- and hydrogen is almost always +1, -2 plus +1 would equal -1. Let's figure that out with water, H2O. If each hydrogen is +1 and one oxygen is -2, +1 + 1, -2 is equal a net charge of 0. What is the charge of this guy? 0. So that's going to be true for just about everything. Hydrogen is almost always +1. Oxygen is almost always -2. Okay. Oh, sure. Now, all group 1 metals in a compound are +1. All group 2 metals in a compound are +2. That's something we've learned a while ago. Group 1 and group 2. They have how many valence electrons? 1. Group 2 metals have how many valence electrons? 2. Where do they want to go? They want to get to either 0 or 8. What's the easiest thing to do? Lose 2 or lose 1. So those are straightforward. Finally, halogens are usually -1, except especially fluorine, but everything else is by context. So going down the table, follow those rules, doing 7 last. But you want to try to find the oxidation state based on those rules. So I'm going to write these down and we're going to break it down. K3P, MgOH2, Fe2O3, 3 1-, CO2, SO4 2-, K ReO4, MgCr2O7, and then Fe3O4. Okay. So I'm just writing these down so I can go to the doc cam. Okay. So starting with this one. None of these are pure elements. None of these are just directly charged ions. So the sum of potassium and phosphorus must equal 0. Well, we didn't have a rule about phosphorus, but we do have a rule about potassium. Potassium is group 1, so potassium is almost always +1. There's 3 potassiums, so it's 3 +1s. Now, because there's 1 phosphorus, it must be phosphorus 3-, so 3 positives and 1 3- would give you 0. So the charge of this guy is going to be +1. The charge of this guy is going to be -3. So if we have a situation where phosphorus has changed oxidation states, if it's gone from 3 to anything else, we can say that's been oxidized or reduced, depending. Same thing, magnesium. This one is actually pretty straightforward. Magnesium hydroxide. We don't really have to do this, but remember hydroxide is -1. 2 hydroxides means 2 -1s. Magnesium is group 2, though, so it's magnesium. So magnesium is 2+. Each oxygen, and there's 2 oxygens, are 2-. 2O, 2-. But there's also 2 hydrogens, each hydrogen +1. So we have +2 -4 +2 again. 2 + 2 is 4. 4 - 4 is 0. So if magnesium is going from 2+ to anything else, or O is going from 2- to anything else, hydrogen going 1+ to anything else. Here's the first one that's maybe really kind of hard. Fe2O3. We don't have a rule about iron. We have to find iron from context. But we have a rule about oxygen. Oxygen is 2-. So 3 O's at 2-. 3 O's at 2- is equal to -6. 2 irons must be what in order to give us +6 to cancel out? 2 irons, 2 times what is equal to 6? So that's going to have to be iron 3. Because 2 times 3+ would give us +6. 6 - 6 is 0. Here's another one that's kind of hard. Nitrate, NO3 1-. The total charge is now -1. It's not going to cancel out to be neutral. The total charge is going to be -1. So oxygen, there's 3 oxygens. Each oxygen has 2-. And we have 1 nitrogen. So now, here's the hard part. If we just use the nitrogen based on what we know about nitrogen, you would say nitrogen should be 3-, because nitrogen typically would want to move to the right 3 places to make it 3-, to make it an octet. However, if that was -3 and you added -3 to -6, you would not get -1. You would get -9. So what number must nitrogen be to give us -1? We have -6 plus X equals -1. And that means nitrogen can only be, in this situation, +5. And that's part of one of the weird things. As I said, nitrogen could go anywhere from -3 to +5. How many valence electrons does nitrogen have? 5. It can't go any higher because it only has 5 valence electrons. Looking at CO2. Pretty common one. CO2. This is neutral. 2 oxygens, each at 2-. 1 carbon. All that adds up to 0. So -4. Carbon has to be +4. How many valence electrons does carbon have? Carbon is group 4A. It has 4 valence electrons. When we make our Lewis structures, it has 4 electrons to make bonds with. Then SO4 2-. So for 2-. this, whatever the amount of oxygens, all this is going to add up to -2. 4 oxygens, each at -2, means we have a total of -8. We have 1 sulfur. X minus 8 equals -2. X minus 8 equals -2. Or you could say -8 plus X equals -2. Either way, the only solution for X is +6. Sulfur is +6 over here. How many valence electrons does sulfur have? It is in group 6A, 6 valence electrons. Moving on, this one is a combination of stuff. We're just getting more complicated molecules, but it really isn't any more complicated. This just made it neutral. So we have 1 potassium. Potassium is +1. We have 4 oxygens. Oxygen are each -2. So far we have +1. We have -8. And this has to add up to 0. So in that case, +1 -8, the net result so far is -7. In order to make this 0, rhenium must be +7. Rhenium must be +7 in this case to make that add up to 0. Another hard one, magnesium dichromate. Magnesium, it's 2+. We have 2 chromiums, let's figure out the charge later, and 7 oxygens, each at -2. We're getting really complicated math now. -14, +2. We'll just say 2x right now. That, whatever this equals, 0. So 2 positive -12, -14 is -12. So that means 2x must equal +12. 2x must equal +12. In that case, x must be 6, because 6 plus times 2 is 12. So chromium is 6+. So I'm throwing some of the hardest ones there. And this one is the mother of all. Fe3O4. Once again, this is total charge of 0. Each oxygen is 2-. We have 3 irons. So if I have -8 and I have 3x, what is the problem here? What is the problem here? Well, 8 isn't evenly divisible by 3. And we don't really have, there's no such thing as a partial charge. So this is one of the actual trick questions, in that this is actually a mixture of iron 3+, 2 iron 3+, and 1 iron 2+. This, you'll never see that on an actual test question, because that is, good God, that's a challenge. It's a mixed oxidation state where iron has 2 different oxidation states in there. This actually forms, iron gets oxidized from the metal into FeO. FeO. And then it gets oxidized. Part of it gets oxidized into forming Fe3O4. And then it finally gets fully oxidized all the way to Fe2O3. But that's a gradual process. So this Fe3O4 is the middling state along the way to forming rust. Oh, shit. Okay. We don't have too many left, so we'll go ahead and go with this. The most common redox reactions, the most common one you could see and the easiest one to directly observe is a single displacement. By nature, all single displacement reactions are redox. Why? There are some combination and decomposition reactions that are redox, but single displacement are always redox. And why is that? That is because an element is being consumed and an element is being formed. Anytime you see a pure element in the reaction, you know this has to be a redox. Why? Why must this have to be a redox? Well, remember, number one rule on determining oxidation state is pure elements are charge zero. Pure elements are charge zero. If that element gets mixed into a compound, it must have gone from charge zero to something not zero. If it went from zero to not zero, the oxidation state must have changed. If the oxidation state changed, there must be a redox process going on. So whenever you see a pure element in a chemical reaction, you should think redox. That should be the first thing on your mind. So many different combination and decomposition reactions and combustion reactions are also redox because they include pure elements. It doesn't mean all of them are. If they don't have a pure element in there, it may not be a redox. So double check. But now here's one thing to keep in mind when you look at some of the homework. Due to the linked nature, whenever something is oxidized, there must be a cause of reduction. Thus, the guy that gets oxidized will reduce something else. And because of that, this mixed nature, the guy who gets oxidized can be called the reducing agent. And the guy who gets reduced could be called the oxidizing agent because it oxidizes something else. In this case right here, aluminum goes from 0 to 3 plus. It has lost 3 electrons because electrons are negative. It is oxidized. Chlorine goes from 0 to 1 minus. It is each chlorine are gaining 1 electron. It is being reduced. So the aluminum is reducing the chlorine, and the chlorine is oxidizing the aluminum, making the chlorine the oxidizing agent and the aluminum as the reducing agent. But so all these are examples of redox reactions. Let's see if we can figure out why they're redox. Some of these, if you can find one element, there's going to be another element. In this case, chromium is going to be going from 6 plus to 3 plus. But that one's not directly obvious. That is really hard to find the 6 plus. We did this one already in the form of magnesium dichromate. But this one's easy. FeO. Fe, if O is 2 minus, Fe must be 2 plus. Then we go to Fe2O3. If oxygen is 2 minus, iron must be 3 plus. If iron is going from 2 plus to 3 plus, it is being oxidized. In that case, something must be being reduced. In this case, it's chromate is being reduced. This is an example of a combustion reaction or a combination reaction, whichever one you want to call it. But this one's obviously redox because you have pure oxygen mixing with carbon monoxide. In this case, oxygen is going from 0 to 2 minus. And carbon is going from 2 plus to 4 plus. This one's hydrogen peroxide. This is a decomposition reaction. We have a compound going to water and oxygen. In this case, the oxygen, the peroxide is being both oxidized and reduced. The peroxide is going from -1 to -2, but it's also going from -1 to 0. So it's going both up and down at the same time. They're splitting apart. Then finally, aluminum plus iron oxide goes to iron and aluminum oxide. Pure element, there has to be a redox. Anytime you see a pure element, you should be thinking redox. And the last thing we could look at is this activity series. This activity series places these redox reactions in terms of reactivity. All these guys, the reason they react is because some of these guys are low energy and some of these guys are high energy. And they're going to try to move to get to a lower energy state. So some of these guys will react directly with cold water. When they react with cold water, they're going to form hydrogen gas. Now, some of these guys will react with acids in a form of corrosion. And some of these guys will not react at all. So up here you see all these elements will react with cold water. Some of these reactions will react with hot water or steam. Some of these reactions will react with acid. And some of these will not react at all with acids. So no matter how strong an acid, they just won't react. So bismuth and copper and silver and mercury and platinum and gold. There's reasons why we use gold and platinum and copper and silver, because these guys are really hard to react. They last a long time. They're not going to just immediately rust away. So that's why some of these are the rare metals. You may have heard of throwing potassium or sodium in water and watching them explode. That has to do with their reactivity. But so not all single displacement reactions will occur. Reactivity can be put into this activity series. The basic gist of it is any metal higher on the table will replace a metal lower on the table. So if I have iron and copper oxide, so iron is right here on the table. Copper is way down there. Iron is higher up, so it's going to swap out for copper. If I try to mix copper solid with iron oxide, we would have no reaction. So one reaction will occur, the other will not. So this little chart could be used to predict whether a reaction would occur. So just a quick example I'm going to throw up, and that's where we're going to stop, is like if I mix nickel with magnesium oxide. So if I said nickel solid plus magnesium oxide, would a reaction occur? Would we get Mg solid and nickel oxide? Question mark. And the question here is, Mg is right here on the table. Nickel is right there. And so would this happen? And the answer is no reaction, because Mg is greater than the nickel. Mg is greater than the nickel, so the reaction would actually go the other way, because Mg is higher on the table. There's going to be probably at least 1 or 2 homework problems about that. But come Friday, we will look at the old test. We will be trying to get everyone ready and figure out when we're going to be doing that test and get that through. I'm going to probably do some sort of in-class thing. Maybe I'll send a survey about when to do that. But we'll talk more about that on Friday. Have a good day.